All right, so I'm gonna pop a star on these bad boys. And then we're gonna talk about a component and a projection between two vectors. Vector projection of V onto U is the vector labeled proj sub U of V. So it's V onto U. Now the notation kind of suggests that, because you kind of look at it as the subscript is U, so that's the one that is below physically in the notation, below the V. So if one is going to be on the other, it would make sense that the one below would be the one that's onto, or being put onto. It has the same initial point as U and V, in the same direction as U. It represents the component of V that acts in the direction of U. All right? So, cool, a lot of words. If theta represents the angle between U and V, then by properties of triangles, then by math, we know that the length of the projection of V upon U is that. When expressing cosine theta in terms of the dot product, this becomes, oh, look at all that wonderful stuff. All right. I didn't understand any of that when I first saw it, and I don't even think I understand any of that after just reading it now. All right, because that's textbook language. All right, my job is to interpret the textbook language so that you have a fighting chance of understanding it. So what I'm going to say here is, put it in simple terms, going back to the two people carrying a piece of furniture up and down a flight of stairs. You have a vector going up in one direction, a vector going up in another direction. They're both contributing to the movement of whatever this object is in this general direction, all right, in the northeast direction, all right? But how much of V is acting in the direction of U? That's what a projection of V upon U is talking about. The other way around would be, I'm going to redraw the picture, just kind of right next to it. Just make sure I do it correctly. Oh, look how shaky that line is. Oh, I didn't put the line draw tool on, so. Classic Bob. Yeah, me too. All right. So, again, I have V and U. Now, if I dropped an altitude going from V to the extension, I'm sorry, U to the extension of V. So I'm going to shoot V up in this general direction. It's going to look something like that. This whole segment going from here to here. So it's beyond, get that, beyond what V is actually doing. What I'm getting is the projection of U upon V. Okay. So basically what's happening here is it's an imbalanced situation, right? Because U is actually contributing more in the direction of V than V is, right? Because if I draw this altitude, I create a right triangle out of it, this is how much, this blue line here, this blue ray actually, is how much U is contributing in the direction of V. And this one is how much V is contributing in the direction of U. You can see based on the blue diagram that U is contributing more to the direction of V than V is itself. All right, so, I mean, I could think of a few examples off the top of my head, but the first one that comes into mind is money. So, kid graduates college, doesn't have enough money to go out on their own, so they live at home with mom and dad. So they're making $500 a paycheck, but their student loans are amounting to, let's say, $2,000. So the kid is contributing, let's say, because they're not going to dump all their money into it, they got to live, kind of. So they contribute $250 per paycheck, so $500 a month to their student loans, but the parents are picking up the other $1,500. How nice of them. All right. That's high school. I'm still paying off my student loans, so I don't know what it feels like to have parents pay for my student loans for me. My wife will be paying off her student loans, I think, until after I'm dead. And unfortunately, I think that's true, because she's like got a solid 30 more years, and her student loans actually cost more than her mortgage. So it's a lot of strain on the heart. So I'm only 41 right now, but you tack on another 20 to 30 years, with that kind of pressure, I don't know how it's gonna play out, but we'll see.
What college you went to?
What's that?
What college you went to?
NYU.
Oh.
It was so cheap back then. It only cost $35,000 a year.
What?
Yeah, that's nothing. Mere peanuts, you know.
70 now?
70 now.
70.
And honestly, I don't look at $35,000 as being cheap, despite what I just said, because I'm still paying it off. Like, that's the thing. I'm still paying $400 a month. And the crazy part is, I have full ride for undergrad. My student loans is all exclusively grad school, because they didn't give the same kind of scholarship for grad school that they gave for undergrad. And so that's that, My wife went to law school. Different story altogether. Yeah, and what? That's the thing. Like, I don't know if anybody's ever been to Disney World during peak season. Like, what happens is, you get to the gate, and if you don't get there early enough, the park is packed. So what they say is, we're at capacity. You can't come in. All right? We gotta let people come out before you can go in. And they do that. It actually goes pretty quickly, because people leave. And I think they leave not realizing that it's going to be hard for them to get back in. But they leave, and then you can go in, right? I think they should do that with professions. Like law school, for example. After the recession hit, and everybody started losing their Wall Street jobs, everybody went to law school and saturated the market.
And now you always see commercials for lawyers.
Now there's plenty of lawyers, but not enough jobs for those lawyers. And so what should happen is the colleges, they should look at the market and say, yeah, we could teach you to be a lawyer, but there's not gonna be a job for you. So we're gonna max out, okay, we're only gonna take, like, I don't even know what the numbers are, but let's say they normally would take 100 incoming law students, which is a low number. We're only going to take 20 this year, because we don't want to put you in a position where you have all this debt, but not have a way to pay it off. I think that would be great. The problem is, there are people, the sense of entitlement, which is like, but I want to be a lawyer. I want to be a doctor. It's like, well, but we're not going to let you, because you're not going to get a job. Like, we're not going to let you throw your life down the tubes. Unfortunately, my wife got a job, so that's great, but I don't know too many jobs that allow you to pay off an extra $1,500 a month in student loans. So between the two of us, it's $2,000 extra. That's more than the mortgage. It's crazy. Right? So yeah, I would love to have had a parent that was willing, able and willing to pay all this stuff for us. But this is the black line here is the starving college graduate. The blue line is what the parent is paying, and you can see that the parent is actually contributing more to the college grad's future than the college grad is themselves. All right? Maybe back in the 80s it was the other way around. Right? 80s, 90s, I don't know. All those folks seem like they're out of debt, so.
It was cheaper back then,
Yeah, everything, yeah.
and soon you keep it for
Houses,
free.
geez.
Houses are cheaper, but the money was expensive. You get a $100,000 house, but you're paying 25% of the mortgage. Now it's $400,000 for the house and 4%.
Right.
Trade it up.
Yeah, that you know, salaries were a lot less than.
Cost of
And
COLA.
yeah, cost
Yeah,
of living,
totally.
food, everything was cheaper.
Yeah, everything. Yeah, so that's the nature of it. But at the risk of doing more math, I think it's probably a good idea because I'm starting to get really depressed again. So anyway, so that's the conceptual representation of the idea of projection, and I think it's a valuable idea. So if you come up with a vector that represents the concept that you're interested in, then finding the projection could give you some really valuable information, right? Now you might look at it and say, well, real life isn't a straight line. We're going to learn about vector valued functions, and those are curves of differing varieties, and we can apply these concepts to those curves. So pretty cool stuff. All right, so how do we get this formula though? Well, I'm going to go back to this diagram. We got a value theta. This is my magnitude of V. All right. And so I'm looking for the projection of V upon U. So I could say just simply, using good old-fashioned SOHCAHTOA, SOHCAHTOTALY, as Mr. Panzer would say, cosine of theta is equal to the adjacent over hypotenuse, the projection of V upon U divided by the magnitude of V. Now the thing is, that projection of V upon U, that's a vector. Cosine ratio, sine ratio, whatever, they're all dealing with lengths of sides, so I'm going to slap a magnitude on this. All right, so what I get is that the magnitude of the projection of U upon V is equal to the magnitude of V multiplied by the cosine of theta. All right. What we did, all us mathematical geniuses out there, not me, the person who invented this, they said, okay, well, I'm not writing that every time, so we're going to call this the component of V acting in the direction of U, which I think makes perfect sense in terms of the name. The notation of it can be a little, I don't know if I like that one very much. But what we can do then is take, so this leaves us, I'll just draw an arrow here because the rest I can just talk you through. The cosine of theta, you're like, oh, where'd that come from? See the previous page where we invented that rule. Cosine of theta is the dot product of U and V divided by the magnitudes multiplied. So that if you clean it up, what we get here is that the projection of V upon U is going to be the dot product of U and V divided by the magnitude of U. All right. So it's really as simple as that. But the projection, the magnitude of the projection is what I meant to say. All right. So that'll give you a component value, but a numerical scalar. All right. So that tells you the quantity. So in this case, it would tell us how much the kid is contributing to the parents. All right. So the kid's paying rent maybe, or that maybe they're picking up the cable bill or something like that. So that vector would represent how much the kid is contributing towards the parent's future, whereas the other one would be how much the parents are contributing towards the kid's future. All right? So this is the actual quantity. Now, if I wanted to determine the projection itself, then all I have to do is multiply this by a unit vector. All right? So projection of V upon U defined the actual vector projection of V upon U multiply by a unit vector in the direction of u. And that's specifically because it's v upon u. How much is v contributing to u? So I want to actually determine what it's gonna be in the u direction. So that's why we multiply it by the unit vector in the direction of u. All right. If it were the other way around, if it was u upon v, then I would multiply it by the unit vector in the direction of v, because there was, from what I've been told, no connection to a larger DC universe.
Oh, no.
So if that's the case, I'm not even gonna spend my $20 a head on that.
No, I'm telling you, it's good. It really, like, it's a really, like, good,
It's like a character study.
it's like, you're gonna like the plot twist. Like, it's really interesting. Like, you're gonna, like, there's some things you're gonna figure out about, like, Joker that you didn't know before. That's like, oh, shoot, that's great.
I feel like yeah, so the cough is back in full force. So page 27. We're looking for the measure of the angles formed by each pair of vectors. So we have v and I. As long as you know what I is, you could find the angle that's formed by the two vectors. So the first thing that you would do is start with the dot product between the two vectors. So positive 3, negative 5, and 1 dotted against 1, 0, 0. And that's just going to give you an even 3. Snag one of these bad boys right now. So the dot product's fairly simple because all you're doing is multiplying each corresponding part and adding them together. Since the other two pieces will zero out, it's just the 3 multiplied by the 1. But I do need to multiply the magnitude, so that part is a little more interesting. So magnitude of v and the magnitude of I. Magnitude of I is equal to 1. I don't need a program or a calculator for that. Instead of bouncing back and forth between calculator and the app here, I'll just do it out. Because it's going to be, I'll write 5 squared. The negative's irrelevant, so just drop it out. So 9 plus 25 is 34, plus 1 is 35, so root 35. All right, so we're getting cosine of theta is equal to the dot product over the magnitudes multiplied, which is 1 times the magnitude of v, which is going to be the square root of 35. So in our calculators, we're typing in theta. Well, it's going to be an approximate value, but inverse cosine of 3 divided by root 35. And again, we're just looking for an approximate here. All right, so I think degree mode is fine. Just make sure you're in the right mode. These questions aren't really calling for any particular mode, so you can go any way you want. So inverse cosine of 3 divided by the square root of 35. And we're looking at, roughly 60 degrees. We can take liberties with the rounding here. All right, because in space it's a question of the idea of where the angle is going to be versus the magnitude of the angular displacement. And so you know, sometimes you just want to have a sense of where the angle is going to be. But in this case, they're actually asking for a numerical value. The reality is, sometimes, you know, it can go either way. If I just need a rough sketch because I want to find a solution for a different kind of problem, then, you know, maybe I don't have to do all this work, because I can easily plot 3, -5, 1, and 1, 0, 0, and get a rough sketch of where that vector would be, or those two vectors would be in relation to one another. And if I don't need to do anything beyond that, then I wouldn't do any of this work, because I could just kind of eyeball what that angle would be. But in this case, I needed to figure it out. Now, vector v is still root 35. V and j is still going to be a simple product. So 3, -5, 1 multiplied by 0, 1, 0. So in this case, just a -5. But the magnitudes multiplied are going to be the same. So this is going to be cosine of theta is equal to -5 over root 35. So the process is kind of getting a little bit simpler. And it'll be even simpler for the next one. All right, so inverse cosine -5 over the square root of 35. Close them up, hit enter. And we're talking about 148 roughly degrees. 0.6-ish. Playing fast and loose with rounding here, but on a test, you just follow whatever rounding instructions are given. Generally, I'm not looking to ding you too much on rounding. Well, I'm never looking to ding you on rounding. It's really just a question of, if you round, just round in the way you intend to round. So if you want to round to the nearest 10th, just make sure you round to the nearest 10th correctly. All right? So, because I've had enough cases where people would say, you said I could round any way I want. I'm like, yeah, but by doing it this way, you said you were going to round to the nearest 100th, but you just did it wrong. You know, just whatever way you decide, round it correctly. All right? And never, ever, 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 ever round until the very last step. All right? So always work with the most exact value until you get to that final step. Otherwise, you're going to introduce an unacceptable amount of variation into your solution. So this is where I'm combining statistical concepts and calculus concepts, because, you know, with that idea that I was talking about before, 21st century concepts, who's to say that you're not going to want to learn some statistics along the way too? All right, but anytime you introduce an unacceptable amount of variation, that's going to be a problem. And you know, the reality is, I like saying that for some reason. I've given the reader the recipe to come up with the exact form of the final answer, or a more exact form of the final answer, and I've indicated that this is an estimate. So if somebody wants to come up with a more precise value, maybe they want to go out to the nearest 10,000, they have the means to do that. They just got to pop this into a calculator. Maybe they want the exact form. They have it right here. Theta is equal to this in degree form, or radian form if they want. So they have everything they need right here. I'm just giving an estimate. All right, so just give the reader an opportunity to know what the true value is before you start estimating. All right, so V and K, well, K, and I'll just make a note here, K is 0, 0, 1. All right, so if I follow this whole progression, I'm going to get the same stuff I got before, except the dot product's just going to give me a 1. So theta, so I can cut to the chase here. is going to be equal to the inverse cosine of 1 over the square root of 35. About 80?
Yeah.
Sounds good to me. So I'll just take that. I won't even put it in. All right, so again, I gave the exact and I gave an approximation, something in the neighborhood of what the right answer would be. All right. And again, we could have gotten a sense of what these values would be by plotting them on paper or in GeoGebra, but numerically we have it too. Now that being said, somebody could go online and prove me wrong immediately. You know, you could look at my review problem sets and find that it was something completely different. But that's where I'm kind of couching it by saying I can't remember the last time. Not like the last time was so far ago. It's like I literally can't remember because my brain does not allow for lots of memories anymore. So bottom line is there's a solid, more than solid chance, I would say better than 90% chance that this proof is going to end up on your unit test. Okay? So what that means, well, from your perspective, put a star next to this process here, like highlight it or something. I don't know. Circle page 27, say come back to this, really important, will be on test. I don't know. So we have a formula. There's nothing wrong with just using the formula. You don't have to invent it every single time. So u dot v, -3 plus 20 plus 3, it's going to be 20. All right. Vector u is vector u, so I just need the magnitude of u squared. Now the magnitude of u squared is the same as dotting u against u. I prefer to do it that way just because I feel like it's less thinking. And if there's one thing I like, it's not having to think. All right, so 1 plus 16 plus 9. So we're looking at 26. All right. So what we have is 20 over 26 multiplied by vector u. So the projection of v upon u is going to be 20 over 26 in the direction of u, which is -143. Simplify 10 over 13. And then run it through the mill, you get -10 thirteenths, 40 thirteenths, 30 thirteenths. I'll put a star on the next one. Actually, the next two. A little word problem there for you. I've had people ask in the past, can we just leave it like this, 10 over 13 times -143? And I say, no, I want you to distribute it through. They say, why? And I say, because I freaking said so. And then that's the end of it. So I just figured I'd save us all from that conversation. Make it easy, right? This is the way I want you to represent the answer. That's all. Okay. Yeah, are they equivalent? Absolutely. Is one better than the other? Hell if I know, right? So, but that's just how I want you to write it. This is one of the very rare instances where I have a particular preference. This is one of them. So, but anyway, just kind of going back to this setup here, I just wanted to talk very quickly about how this formula came into being, because the first piece of it is, so the v multiplied by u dot v over, that's all the part where you're coming up with a component. This last little bit here, this guy right here, is the unit vector. In the direction of u. All right, so just a quick review, because again, either I forgot to go over it or I went over it a while ago. Unit vector, all you're doing to determine a unit vector is dividing a vector by its own magnitude. All right, and so that's just giving you a vector with a unit length of 1 in the same direction of the given vector. All right, so what it does is it allows us to develop a basis for a particular system. All right, so I now know what the vector would be in the direction of u for this system that has a magnitude of 1. All right, so if I were to carry this out through the magnitude process, whether it's by hand or in your calculator, that's going to give me a magnitude of 1, and that's the whole point. Or 1 multiplied by the component is what I mean to say. All right, numbers 12 and 13, well, 12 is along the same lines as 11, except it's in 2 space, so it should be easier to do. Number 3 looks like it would be a lot harder, but it's actually not that bad. It's just, you throw words into a problem and people start freaking out. So by all means, freak out and either do it or don't do it, but we'll go over it next class. But I want you to at least attempt, or I suggest, recommend that you attempt it first before I just take you through the process, because I don't want to steal all the thinking moments for this kind of question. Let you kind of wrestle around with it first before I be proactive here. All right, so at a minimum, if I'm looking for the projection, all I'm looking to do is follow a formula. You look at it this way. So the projection of v onto u is going to be this model carried out. So I just got to do this work. That's not bad. All right, you don't have to invent the formula every step of the way. I don't know if I should just give it away or not. I'll just put it this way. I can't remember the last time on the unit test that the proof wasn't this one. When I make bold statements like this, I try to make sure that I'm not lying by immediately putting a reminder to myself in my, I have a little to-do list in my, I'm old school, believe it or not, this is considered old school. Sending an email to myself that says, with a subject line, to do. And then I just keep it as new for like a long time. So generally I always have a minimum of one new message in my inbox at all times. Okay, so Calc 3, page 27, proof. Because I've also gone down that road before where I emphasize some important point in class. Be like, you damn well better study this. It's going to be on the test. If you don't study it, I don't know what you're doing with your life. And then I forget to put it on the test, and then people are pissed at me. So I try not to do that. So yeah, the reason I bring that up is because you don't have to, when you're dealing with a problem like this, numbers 12 and 13, you don't have to invent the formula for the question because I'm going to be asking you to invent it somewhere else. All right? Here it's just a matter of using the formula. All right? So the projection of v upon u is just following this idea. Now there's the whole right triangle trig origin story behind this formula, but really it's just a matter of finding the dot product of u and v. It helps to identify what u and v are. I'm going to write it in component form. When we get to vector valued functions, you're going to see why the ij notation could be a little bit more useful. So I need u dot v, and I need the magnitude of u as a quantity squared, which is the same as saying u dot u. That's one of the properties. All right, so u dot v is going to be 1 times 3 plus 6, son of a, 6 times negative 2 is going to be negative 9. And the other one is u dotted against itself, so 1 times 1 plus 6 times 6. So 1 plus 36 is 37. All right, so if we go back to our formula, we're taking that quotient and multiplying it by vector u. All right, so once you have those two calculations, there's really nothing to it, because the projection of v upon u is going to be negative 9/37 times vector u, which in this case is 1, 6. All right, and then we just run it through the mill. All right, so just distribute. Negative 9/37. And then, well, it's not going to simplify, so negative 54/37. All right. So nothing terrible there. We're following the process. But inventing the formula could be a little kookier. So then we have a word problem. Word problem is really just what we just did with a little bit of context. But anytime I introduce angles, it oftentimes, most of the time, means that you're going to have to discover what the component form of the vectors are going to be first, before you can get into the process of finding a projection of one vector upon the other. All right, so a container ship leaves port traveling 15 degrees north of east. So that's all labeled in a diagram, but I'll read it anyway. This engine generates a speed of 20 knots along that path. All right, so I'm just going to make a little note that vector v has a magnitude of 20. All right, in addition, the ocean's current moves the ship northeast at a speed of 2 knots. All right. Considering both the engine and the current, how fast is the ship moving in the direction 15 degrees north of east? Round the answer to the nearest 2 decimal places. All right, so so we're looking for a vector relationship, a projection of one vector upon the other. So there is a projection of one vector upon the other. It's just a matter of working that into the process. All right, so again, container ship leaves port moving 15 degrees north of east. So that's actually happening. Its engine generates a speed of 20 knots along that path. So that's what the engine is doing. That doesn't necessarily mean that's how fast it's going. All right, the ocean current contributes a speed. Now the ocean current moves at two knots, but it's contributing speed also in support of the boat moving in the direction of 15 degrees north of east. All right, so what we want to figure out is not like a vector sum or anything like that. We just want to figure out what the projection of W upon V would be. All right, so here's W. That's giving a magnitude of 2. All right, so what I want to know is the projection of W upon V. All right, but more so, it's actually not telling me to determine a vector. It's just asking me to determine a magnitude. So this is asking me for the component of W acting in the direction of V. All right, because I already know which way it's going. I want to know what the magnitude of that final displacement, the velocity would be. All right, so what I want to do is I want to kind of just grab my process from above, then use my new terms or my new variables to make it fit this situation. All right, so I have u dot b over u squared times u, but that's the whole shebang. All right, what I want is the component form of it. All right, the component form, because I don't need the unit vector part. The component form is u dot b over u, the magnitude multiplied uv, but then the v's would cancel. So we just want the part that's u dot v over u. All right, so, but again, that's the projection of v upon u. All right, the component form. So that's what I want to reproduce down below. And that's what I'm going to do. So the component v upon u all right, so again, all I'm doing is I'll just highlight it. I'll bring it back in a sec, but I'll highlight it for you. This part here is the component form, which corresponds with this piece. All right, that's the component. Oh, that is not a marker. I don't think there's any way I could keep it all visible at the same time, but I rewrote it, so I guess it's fine. All right, so I just want to match that up. I just want to match it up with my new scenario. And there's nothing wrong with changing your variables. If you want to make it U's and V's instead of W's and V's, that's fine. But basically, in the expansion, W is going to take on the role of V, and V is going to take on the role of U. All right, so if I have those values, I'll be in good shape. All right. Now the issue here is we got a couple more steps to go, but we're on the right path here. I need the dot product of V and W, which means that I need to do some work to find those values, but that's going to be easy enough. The magnitude of V I already have, that was given. So I could chuck that in right away. I don't need a bar that big. Said no one ever.
the V, because we have an angle, and I think I'm just debating the whole like turning the calculator off and back on thing, but I think I'm just going to leave it because I don't want to turn it off to put it back on. So angle, magnitude multiplied by the cosine of the angle, comma sine of the angle. So 20 cosine 15. So 20 cosine of 15. And the sine of 15. But these numbers are what make it a calculator problem rather than a unit circle type problem. Because even though 15 degrees is something that you could figure out with some indifference identities and things like that, it's not something I'd ever ask you to do. W is equal to 2 times cosine 45 sine 45. All right, so I could just do the dot product of V and W. Now, you can do it on the fly if you want, or you can just kind of mentally handle it. But essentially all you're doing is running through with the 20 and running through with the 2 and then taking the dot product of the two vectors. So I'm just going to write it out before putting it in the calculator, but this is going to be 20 cosine 15 plus 2 cosine, times multiplying corresponding parts, 2 cosine 45. I caught myself doing a vector sum there for a second. Plus 2 times the sine of 15, or sorry, 20 times the sine of 15. Times 2 times the sine of 45 degrees. All right, so that would be our dot product. It's going to be ugly, but it's doable. So I'm just going to pop it in. 20 cosine 15. 2 cosine 45. 2 cosine 45. One too many parens there. I'm going paren overboard here. Plus 20 sine 15, close them up, 2 sine 45, close them up. So we're getting that. So about 34 and change, 34.641, etc. Barring any mistake on my end. All right, we're going to take that value and divide it by 20, and we're going to get that, like 1.732-ish. All right, so this value, I'm going to denote it as V dot W in my formula, because again, I don't want to round to my last step, so I wouldn't want to put in there that we're looking at 34.6, for example, to divide it by 20. So I'm going to get 1.732 and so on. They want to know how fast is the ship moving and round it to the nearest 2 decimal places. Well, it's already powered to go 20 knots. So the current is giving it a little boost of 1.7 knots. So we're talking 21.732, blah, 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 a bunch of other values. So the final answer would be 21, because they said 2 decimal places, 7.3 knots. I give you the short way. So the last thing we're going to do tonight is called a cross product. It's pretty crazy stuff. And in fact, the derivation of it involves a system of equations. It's really quite incredible. I'm just going to give you the basics of it. We're not going to go through the whole thing, the whole derivation, which also means that you're not going to be responsible for the derivation on a test, just because it takes up like a whole page of your notes if you were to do it out completely. But I want to give you a sense of what the setup is and how you would go about the process. What a cross product will give us, and by the way, next class we're going to merge ideas, dot product and cross product put together, which is going to give us something known as a triple scalar product. Very exciting stuff. Also known as a determinant, right? So a little connection between linear algebra and this course. Anyway, cross product, you start off with 2 vectors. What it'll do is it'll give you a third vector that's orthogonal to the other 2. So if I have 2 vectors going out in space, the cross product is going to give me the third vector. Now that third vector could be going, based on this, upwards, or it could be going downwards. All right? So either way, it's going to be perpendicular or orthogonal, depending on your perspective, to the original 2 vectors. All right? So orthogonal, well, that sounds an awful lot like a dot product. What this is telling me is that U and W, so I can just draw a quick sketch, really. Here's U, and here's V. So there's some W that's coming off of the intersection between these 2 vectors, such that it's perpendicular to both.
What about going the other way?
It could go the other way, but I'm just going to draw it this one way. But it could go downward also. All right, so what we're going to get through this process is 2 different vectors, but generally we just need one of them because the other would just be the negation. All right, so once I find one negated, I have the other. All right, so as long as you could learn the technique for finding one of them, you're in good shape. So this is my W. Purple is. So using a dot product, I would say U1, 2, and 3 dotted against W1, 2, and 3 is going to result in a value of 0. All right, because one of the things we learned earlier is that the dot product, if it's equal to 0, the 2 vectors are orthogonal to one another. All right, I can distribute this out using the dot product. U1, W1 plus U2, W2 plus U3, W3 is going to be equal to 0. But I also have V1, V2, and V3 dotted against vector W. That's also going to give me a 0 as a result. So V1, W1 plus V2, W2 plus V3, W3 also equal to 0. All right. Now, ultimately, what we're looking to do here is figure out what W1, 2, and 3 would be in terms of U1, 2, and 3, and V1, 2, 3. All right, so through all of this mess, what I'd have to do, it's kind of terrifying when you think about it, but I'd have to solve this for W1, 2, and 3. Because that's going to be the cross product. That's the definition of the cross product. And you can see, I mean, it's a mess. Because we have to use substitution, solving, you know, pick a variable, it doesn't matter. Like solve for W1, for example, and replace the W1 here with that. Simplify, clean it up, see what you get. Hopefully some other things would cancel out. Because you're going to be replacing a W1 with a W2, W3, so you should be able to consolidate some things. All right? Maybe you have to do an additional substitution. It gets pretty crazy. I'm not exaggerating when I say that it's an entire page of your notes to carry out this process. All right? But just the setup is all you really need in order to understand that this is something that will work. Because ultimately, if I'm solving for W1, W2, W3, it's going to give me expressions that are in terms of U1, U2, U3, and V1, V2, and V3. All right, so this first piece here is the same as my W1. This piece here is my W2, and this piece here is my W3. Now, one part of it that you may not feel 100% comfortable with is the sign change component. The W1 in the cross product is always represented as a positive. W2 is the negative, and W3 is going back to positive. It's alternating in sign. That actually has to do with permutations, so thinking back to probability and statistics and things like that. The different ways in which you can arrange the elements of these vectors. It bears out that some permutations are considered to be positive permutations and some are negative permutations depending on the way it's arranged. And so that's a whole other explanation and concept. So I go through that in my linear algebra course. I believe I'll be doing that in tomorrow's linear algebra class. So yeah, so if you want more on that, you can check out that video. Right? So you just gotta go to my linear algebra class list or playlist. I mean. Right? So I'll talk about the right-hand rule in a few minutes once we do the computations, but it's actually pretty easy. There's a nifty shortcut to help us determine the cross product. I'm going to take you through that because writing it this way, I mean, it's fine, but then it's very easy to get crossed up. No pun intended, because you look at it and say, okay, well, which one's U2 and V3? Ah, crap, what am I looking at here? But if you use what we call cofactor expansion, also a linear algebra technique, it does kind of give you a little bit better of an idea of how this is going to play out. So what we do is we arrange our vectors as row vectors. All right, so you can, in a matrix, you can represent your vectors vertically or horizontally, as long as you're consistent, and each way will have different meaning. This part is kind of weird. I, J, K are actually vectors themselves, so you actually have a vector within a vector. That's strange, but that's a different conversation, again, for a different day. So what we do in order to determine the I coefficient is identify the I row. All right. When you identify the I row, what you're going to do is you're going to take the elements of I row and column. You're going to take the elements that make up the matrix that are not in that row or column. All right. So basically, I'm just crossing out the row and column that I exist in, and then just creating a matrix out of that. All right. And I'll show you how to handle that in a second. But then for J, I'll do the same thing. I don't want to mark up this diagram too much. I would cross out the middle column and the top row, and I'd be left with U1, V1, U3, V3.
All right, so that gives me that one. And then the same thing for K. If I wiped out the row and column that K is in, I'd have U1, V1, U2, V2. Right? So that's where these entries are coming from. So really, as long as you know to set up your matrix this way, then these are going to build themselves. All right? And then it's the question of what do we do with that? So I'm going to take you through an example and you'll see. All right? So we're finding the cross of P and Q, sorry. I, J, K. Undo. -1, 2, 5, 4, 0, -3. All right, so I'll use a highlighter here. So I'm looking for I. So I'm going to wipe out the row and column that I is in. So, and then turn my highlighter off. 2, I might as well go blue. Those keeping score at home. And I'll do the same thing for J. So -1, 5, 4, -3. And then I guess red. So same thing for K. -1, 2, 4, 0. All right, so to find, we're looking for a determinant here. The vertical lines around a matrix is looking for the value of the matrix. It's asking for the determinant. You do it one of two ways. In your graphing calculator, or diagonal down minus diagonal up. For a 2x2 matrix, this is, it's easy enough to do by hand. What I mean by diagonal down is multiply, starting from the upper left and going to the right. The diagonal going downward, multiply those two values, and subtract from that the result from when you multiply the diagonals going up. All right. For anything other than a 2x2 matrix, that process won't work. But if I'm looking for the cross product between two vectors in 3 space, it'll always be a set of 2x2 matrices. So this technique will work. If you don't want to do that, that's fine. You put it in your calculator. There is a determinant function. The problem is you're putting in 3 separate matrices in order to find the determinant, and that's kind of annoying. All right, doing it once or twice is okay, but once you hit the 3rd time, you're like, and especially if you have a bunch of problems to do related to it, it could be kind of nightmarish. All right, so the diagonal down values, -6 minus 0, those are going to be the coefficients of I, minus 3 minus 20. Diagonal down is -1 times the -3, which is +3. 4 times 5 is 20, subtract the 2. Plus, diagonal down is 0, minus 8. And that's the K. I missed the J. And there's the K. All right, so we're looking at -6I. 3 minus 20 is -17. Negative, negative, so plus 17. Minus 8K. Or you could put it in component form. You could write it as -6, 17, -8. Either way.
Oh, I think I see what the problem is. Here, browser. It definitely is. All right, so that is the relationship. All right, and I'll show you where that comes from in a minute or two. Number 6, my tendency would be to go the other way, because I look at it as and say, okay, in order to find theta, I'd have to first find the angle. In order to find the sine of theta, I have to find the angle between these two vectors, which may or may not be easy. And then after that, I got to use this formula by finding the magnitude of each of these. So at this point, I'd be like, you know what? Let me just do the cross product. So I, j, k, 5, 2, -1, 0, -1, 4. All right, so you're adapting to the situation, really what it comes down to. All right, so for I, again, I'm ignoring the I column and the I row, so 2, -1, -1, 4. And then maybe as you go, run your calculation so you're not overwhelmed with it. All right, so this is going to be 8 minus a positive 1, so 7i. Ignore, for the second one, ignore the j row and column, so 5, -1, 0, 4. So that's just a 20, right? Because on the diagonal up, 0 times -1 is going to be 0. So diagonal down is 20, so minus 20j. And then for the k, ignore the k row and column, so 5, 2, 0, -1. So again, we have a nice looking 0 in there, which means the diagonal down is the only thing I'm caring about, so -5k. All right, so that's the cross of A and B, or U and V if you want that notation. All right, but this one's a little weird because it's not saying find a vector orthogonal, it's saying find a unit vector orthogonal. All right, so what I need is the magnitude of A and B, A cross B. So 49 plus 400, so I'm squaring each, plus 25. So 474. And so the unit vector is going to be A cross B over the magnitude of A cross B. Can I simplify the rad 474? I don't know. Maybe. I don't want to, so I'm not going to. And I'm going to put it in component form. So rad 7 over rad 474. -20 over rad 474. Now, just for clarification, if it was the square root of 25, 625 even, you know, like something that's a perfect square and you know it, yeah, get the result. But 474, it could be, maybe it's not, but this isn't a computational skills course, so I'm not looking to take off credit for funky radicals not being simplified. All right, but one thing you can do if you're not sure, and again, this goes back to that program in my linear algebra course that I posted for magnitude. Maybe you write that program because a unit vector should have a magnitude equal to 1. So pop these values into that program and see if it gives you a magnitude of 1, because if it doesn't, then you did something wrong, because it's not a unit vector unless its magnitude is equal to 1. All right, so finding a cross product when you're dealing with the unit vectors is not terribly difficult. But it's not always the kind of thing that you necessarily want to do by hand, right? So what we get from this, I mean, we look at the properties. We have the anti-commutative property, which is a nice one. We have distributive property, which is telling us that if we have a vector sum, we could distribute a vector across of a vector through that sum. And then we also have something like
multiplication by a constant. And so if you look at this one, kind of weird. It tells us that we could take that c and multiply it by the u and then cross it with the v. Or we could take that c and multiply it by the v and then cross the result with the u. Right? But it's essentially telling us that we could do it in whatever order that we want. Right? So the reverse would also be true. So in the first example here, what I could do is I could pull out, let's say, the 2. All right, so following that idea, you know, because I'm looking at the 2 as being my c value, I could look at this as saying 2 times I cross j. 3j. Cross the j that's already there. But then, using that same property again, I could pull out the 3 and get 2 times 3 with just the I crossing with the j. Right. So now really it's just a matter of figuring out what I cross j is. Because if I could figure that out, I have a scalar multiple. Scalar multiples can be held on to until the very end. I can cross this up, I cross j, result cross j again, and then multiply the result by 6. 2 times 3 is going to give me the 6, and then I'll have it. It's just a matter of knowing what I crossing with the j would give us. All right, so we could do it by hand, but you could also use a more intuitive approach. So let me just draw, yikes. Famous last words for me anyway. Let me just draw. It's like it never ends well. Whoa, I just discovered something that I didn't want to discover. So here's my I. And there's my J, and there's my K. All right, and I'm going to attempt to hand sketch in what the negatives would look like. So here's negative K. Negative J, negative I. All right, if you have a general sense of what the I, J, K axes or the X, Y, Z axes look like, then you could kind of piece together what you're looking for. So the cross product, by definition, is a vector that is orthogonal to two given vectors. All right, so what we're looking at is I and J, and so in the case of I and J, we know that if we're going to cross them, the result is either going to be in the positive K direction or the negative K direction. It's just a question of which is which. All right, so we talked about different ways to manipulate our hands last time, and I ended up not demonstrating the most dexterity whatsoever that could be demonstrated, I guess. Some of you are better than I am, but the one way that I kind of settled on as being the way I like the most is that if you have your index finger going in the direction of one vector and your middle finger going in the direction of the second vector, then the thumb is going to point you in the direction of the third vector. All right, so I can't do that physically for I going towards J because that's just not how my hand works. But I can do it for J going towards I. All right, so I can do that and also use the anti-commutative property. Because if I know what j going towards I would give me, that would be the positive k that would be going upward, then the other way around would be the negation of it. All right, so that's something that I can settle in on and be fairly comfortable with. All right, so the other approach, at least until you get comfortable with it, is what we call in the education industry straight up memorization. And I'll show you what I mean by that. First, it starts with a little discovery on your part, but then it becomes, okay, well, I've done this enough times that I'm just going to straight up memorize it. Or, you know, put it on your index card. Let's get rid of that. Of course, it would help if I typed it in correctly. So, typing it in and then I'll pull it up. Let me pause this so we can record while I'm doing that. Computer. Yeah. So, I think I misspoke a second ago and I said the wrong room. It's digital ink in here. I think I said negative k. It should be positive k because this is not my right hand. Fun fact. I've been trying to make myself a lefty, and this is where I end up. So. Try it again using the appropriate hand. So, problem is I can't really lift my right hand. So that's the other problem. All right, well anyway, I jokingly said straight up memorization. That could be part of it. So I plotted I plotted j, and then I did the cross of I and j on GeoGebra. I got rid of the axes so it would be a little easier to see. And then I put the vectors in. The cross is k, 0, 0, 1. And so you can kind of see it there. The other one was the, you start with the pinky going along the vector, the initial vector. And when it's on GeoGebra, it's a little easier to see because I can kind of manipulate my hand in the right direction. But again, I'm trying to do it with the wrong hand, so that's kind of the issue. But you can kind of manipulate your hand to do it the right way. So that's a little, a little bit in your territory, up to you how you want to handle it. But generally speaking, I would say that it would make a lot of sense that if we're defining the z-axis as being the third dimension coming up from the xy plane, that would have to necessarily be the cross product between those two vectors that are themselves orthogonal to one another, because we're defining an entire dimension based off of that, those original two dimensions. All right, so in that regard, it should kind of play out. But there's also the mathematics behind it. But GeoGebra is going to help you in that regard also, because let's say I wanted to cross, let's say this would be, you'd kind of have to keep it in your mind that this is I, this is J, and this is K, but you could also make the change. You could define this as I. I would go capitals because lowercase, GeoGebra has a hard time with that. But you could actually cross A with C, for example, and see what you get. That would be the cross of I and K. So cross, cancel. Can't just type it anywhere. Cross
I would say A and C. And so when I put the vector there at D, it looks like it's plotting it in the negative J direction. All right, so you can kind of get that information that way. So GeoGebra is good for the visual. The right-hand rule is a little iffy, especially if you don't use your right hand like I did, or didn't. But I'm going to chalk that up to the illness. But whether you use the palm and, you know, closing your fist from one vector to the other to demonstrate where it will go, I mean, if that's the case, it's pretty easy. It's just, you know, maybe if I scroll it down a little bit, it's just, I can't get it. Well, that's like literally the least helpful thing. I just want it lower on the screen. That might be the best I can do. Because my issue is I can't really lift my arm, but if I have it here, so along this vector, you can see vector A is my U, if I want to, and U is in the direction of X, 1, 0, 0. If I close my fist in the direction of the other vector, you can see it's moving towards the positive J. All right, so it's just harder to do it with the two fingers. You know, I can demonstrate that also, but you know, V's all the way over here. I'd have to really kind of split my finger apart in order to do it. But I mean, I guess you can kind of see it. It's when things go negative, that's when things become difficult. So what I say is, hey, take the brand of the right-hand rule that you like, apply it in the way that fits the problem. And if you got to use the anti-commutative property to make it work, then that's fine. I mean, in fact, that's encouraged because it's demonstrating knowledge of the property itself. What's that? It's along the U. I just made it disappear because it's like distracting. What's that?
How would we get negative C?
Oh no, it was I misspoke earlier. It's supposed to be positive. Yeah, that was what I was saying before when I was using my left hand to demonstrate the right-hand rule.
Would we get negative C?
What's that?
How would we get negative C?
You would get negative C if we were crossing V with U, the opposite direction. All right, so if I were, so in this case, my right-hand rule is telling me that U going to V, so I close my fist in the direction of V, it's pointing upwards. But if I were going V in the direction of U, I'd have to contort my hand in such a way that I'd be, you know, at the upside down, inside out, kind of, it's like a pain in the ass, so I don't even bother. But the reverse is going to, I'll show you the rule. HDMI 1. The reverse process is pointing to what's known as the anti-commutative property, which is if you swap the order of the cross product, it's always a negation. So if I know that U cross V is some positive value, then the opposite way of crossing it would produce a negative value. All right. So long story short, and you know, it sucks because physical limitations every semester. I mean, you can listen to every one of my videos for every year, every semester that I taught this course, and you'll hear me fumbling my way through an explanation on these particular questions, just simply because I can't get my hand to work the way it's supposed to. So that's the one thing, like GeoGebra can be a resource, but that resource ends up being in the realm of just developing the understanding so that you can not have to figure it out every single time. All right. So K crossed against J. So this is the same as 6 multiplied by K crossed against J. Now, if the cross product of I and J gave us some variation of K, whether it was positive or negative, then you could expect the same relationship to hold for K and J to give us some kind of I. It's just a question of how that's going to play out. Now, worst case scenario, and I'll show you in the next one, I'll actually do the cross product out with you, because like in a gen, you could always just figure out the cross product. It sucks, but not when there's a bunch of zeros in it, you know, because zeros are a wonderful number. K crossed with J, again, it's just a matter of somehow contorting your hand to make it work, all right? I can't physically get my hand to do K cross J, but I can get it to do J cross K. So I can do it like this. And when I do that, it's pointing out in this direction. So the dotted is going into the page. So that negative I is not what I'm going to get as a result. Coming out of the page is I. All right, so J cross K is I, but I want the opposite of that. All right, so if I'm getting J cross K to give me a positive I, then K cross J should give me the exact opposite of that, which would be negative I.
The next figure has to be the first one.
Yeah. Yeah, the first vector, or your pinky finger, if you're using the fist closed technique, or you're using this one. If you're using this one, then index finger is the first vector, middle finger is the second vector. First finger, first vector, second finger, second vector.
Got it.
Oh, it's K cross J.
J.
Yeah,
Probably
I
I.
misspoke, but it's still going to give you I.
I.
J cross K will give you an I, but since we want K cross J, we want the opposite of that.
All right, so the result here would be negative 6I. All right,
So, like I said, you can kind of figure it out based off of these properties, and if it makes sense to you, great. If not, then you need something else, and that something else could
actually be figuring out the cross product. All right, so I know the directions here say to use the cross product properties to figure this out, but I'd rather give you a couple of alternatives. So let's figure out I cross K. And actually, it's a nice kind of simple-ish review. Simple in the sense that it'll be fairly easy. So we're looking for the determinant involving, you still need to know what the vectors I and K are. So 1, 0, 0 and 0, 0, 1. All right, so we're looking at I minus something J plus something K. It's going to be something I, that's why I left a space, but you don't have to actually put parentheses as placeholders. I just, at least for the second and third terms, I tend to do that. All right. So for the I, we're going to ignore the I row and I column. That's actually not entirely conceptually correct, but that's just the way I'm explaining it. So there's a whole really unit in linear algebra where we get into why this works the way it does. But we're finding the determinant of what remains. So diagonal down product minus diagonal up product. In this case, 0. And we do the same thing for J. So ignore the J row and column. And then we find the diagonal down product and the diagonal up product. So we're looking at 1 times 1, which is 1, minus 0. And then for the K, diagonal down product minus diagonal up product, it's going to be equal to 1. 0. All right, so what we get from this is a negative J. All right.
So I cross with a k is going to give me a negative j. Right? Now, if you go and verify that with the right-hand rule, it should bear out. So I can't physically do, with the right-hand rule, I crossed with a k, but I can do k crossed with an I. K crossed with an I would point me in the direction of j. That's the opposite of what I want, so I would take the opposite of that. So I would get a j by doing the exact opposite of what I'm looking for, so it must be negative j that I'm looking for. All right. So you can carry it out the process that way, and then do the same thing with k cross j. K cross j, again, I can't do physically k cross j, but I can do j cross k, which would give me a positive I. Now that one I'm not going to do out because we kind of sort of addressed that one already. So whether it's from the right-hand rule or from the fact that we figured out k cross j in the last question, we could say k cross j is equal to negative I. And so I'm looking for negative j crossed with negative I. All right. So I can't physically do negative j crossed with negative I, but I can do negative I crossed with negative j. So with the right-hand rule, that would point me out of the paper. So it's just a question of understanding what out of the paper means. All right? Out of the paper for me means the solid lines. All right? So anything that my thumb is pointing out of the paper, that's going to be I, j, or k, depending on what you're looking for. All right? The opposite of those would be the dotted lines. All right? So if negative j getting crossed against negative I, so I can't do that, but I can do negative I crossed against negative j. It's going to come out of the paper. That would give me a positive k, so I know my result would have to be negative k. All right, because I'm looking for the exact opposite. All right, so I mean, it's a question of just how nifty the shortcut is if you don't understand what the hell I'm talking about. You know, shortcuts are wonderful if you can make use of them. But what I demonstrated over here is that even the long way of doing it isn't going to be that bad. So let's say day of the test, you forget about this whole right-hand rule business. You're like, all right, I kind of, sort of, maybe was on the verge of understanding it, but then I lost it. Let me just do it. There's going to be a lot of zeros in there. So you're going to get either a positive j or negative j when push comes to shove, so you're going to be in pretty good shape. And in a lot of cases, you kind of drop out a lot of information, because if you know that the cross product of I and k is going to be some kind of j, then you really only have to worry about the j column, or at least eliminating the j column and working from there. Same idea for k and j. You know it's going to be some kind of I. Work only on the relevant parts of the determinant and you'll be good. All right, so it's kind of weird. All right, so the last thing we're just going to take like 10 seconds. That's an exaggeration. I'm just going to talk to you about where that area of the parallelogram business comes from. So we locate vectors u and v such that they form adjacent sides of a parallelogram, kind of like a vector sum. Find the area of the parallelogram given by the magnitude of u and v, or u cross v. All right, so the derivation is very easy, because area of a parallelogram is base times height. All right, and I labeled everything in the picture for you. All right, because these are vectors u and v, but we need the magnitudes if we're talking about the length of sides. All right, so the theta part, if I needed the height, I'll just call that h. Sine of theta
is equal to opposite over hypotenuse. And so that actually gives you v times the sine of theta. So h, which you define as your height, is really the magnitude of v times the sine of theta, just by knowing simple unit circle trig, SOHCAHTOA kind of stuff. All right. The length of the base is equivalent to the magnitude of u. The height is the magnitude of v times the sine of theta. So as it turns out, we have a proof that demonstrates that, yeah, that formula that we're using to and defining as the magnitude of the cross product will also give us the area of a parallelogram, right? In 2 space, 3 space, or 10 space, it doesn't matter, all right? So I'm gonna pop a couple of stars, and that's it. That's why I said it would take like 10 seconds. I'm gonna pop stars on 7 and 8. And that's where we're going to leave it for tonight. That's unfortunate. Area of a triangle is half the base times the height. All right, so somewhere along the lines you knew this. So what that means is that a parallelogram can be thought of as 2 adjacent triangles. Now, those 2 triangles have to be congruent. All right. So the bottom line is you have everything you need. It's just a question of kind of putting it together. All right. So in this case, what I'm going to do is I'm going to figure out what the triangle would have to be if it were half of a parallelogram. All right. So I'm just going to create a parallelogram out of it. All right. So the whole shebang would look like this. I'm just creating a rough sketch of a congruent second triangle, just kind of floating in space. If that's the case, then I have a lot of different options here. I could pin it at P and make it PR. And PQ. All right. So PR would be -1. I'm just subtracting corresponding parts. 0. Ripes. 1. And PQ is going to be -1, 1, 0. All right, so I'm just going to go through the process again of finding the dot product between the 2. Divided by the 2 vectors' magnitudes multiplied. So dot product's not bad. 1 plus 0 plus 0. Now the magnitudes, we have to figure those out, but they're not terrible either. They're just not as clean as maybe something that's living along the x or y axes. All right, so the square root of the squared values, we're looking at -1 squared, which is 1, plus 0 squared, which is 0, plus 1 squared is 1, so √2. So PQ has the same ingredients, So it's going to have the same result. All right. So we're looking at root 2 multiplied by root 2. So cosine of theta is equal to 1/2. So this one's going to be more exact than the previous answer. So you could actually work with it in its exact form, but I'm going to take you through the same approach because I see the value in it. That and other reasons. So area of the parallelogram, I could just do the two parts multiplied, the two vector magnitudes multiplied by the cosine, the sine of the angle. But I'm going to find the area of the triangle, so I don't need the whole shebang. So, but let me just clean this up a little bit. Let's say you're a little iffy on your unit circle trig / you don't even want to bother with it because you can use the calculator to come up with a decimal approximation of the area anyway. I could call this theta is equal to the inverse cosine of 1/2. All right, the fact that you know that that's equal to pi over 3, that's fine, that's great. I don't want to say that that's just fine, it's wonderful, it's good news. You can get away with that without knowing that in this particular situation. All right, so the area of a triangle is going to be half of the magnitudes multiplied, so radical 2 times radical 2 times the sine of the cosine, inverse cosine of 1/2. So radical 2 times radical 2, this is actually something you could do completely without a calculator, which is kind of cool, but you know, if you did use a calculator, you get it also. Radical 2 times radical 2 is 2, half of which is 1, so forget that. Inverse cosine of 1/2 is pi over 3, or 60 degrees. Sine of pi over 3, or 60 degrees, would be radical 3 over 2, which is approximately 0.8660, which is even more approximately like 0.9. I mean, if you really want to approximate it, you'd say 1, but square units. But that's what your calculator would bear out, which is good because if you know your unit circle stuff, then you don't even have to pick up the calculator. But if you don't, there's no unit circle penalty on tests. The only time there's a unit circle penalty is on unit circle quizzes and unit circle bonus assignments and things like that. All right, but on a test, you always have your calculator, which is the reason why some of you are taking this particular class with me. Yeah. So yeah, that took a while going over those quote-unquote homework problems, but they're so important to what we're going to be doing moving forward that you just couldn't skip it. Okay? And I didn't want to just leave it to an answer key, okay? Because we got to do some calculus with this stuff, and that part is it's coming. We got to be ready for it. Right, but if you don't understand the underlying structures, like how are you going to do a derivative or antiderivative when it comes to vectors, functions that are contained within vectors, if you don't understand the vectors themselves, right? So that's the idea there. Triple scalar product is kind of fun. You can see that you're dotting against a cross product, which is kind of interesting to think about. But really what you're doing is finding a determinant, right? In effect, you're finding, if you're thinking about a cross product, the magnitude of a cross product giving you the the magnitude of a cross product giving you the area of a parallelogram, then what the triple scalar product, because it's giving you a third dimension, is actually going to give you the volume of something known as a parallelepiped, which we explored, right? That was the first tech assignment. That three-dimensional parallelogram, that was a parallelepiped. And so that's a parallelogram in 3 dimensions. This will give you the volume of that. right? So determinants are, almost usually exclusively limited to linear algebra, but we can use it also to find areas and volumes, all right? The good news is, you look at this, it looks pretty nasty. You got to find a cross product and then a dot product after. That could be pretty funky, but not the way I'm going to show you. So if we're looking for the triple scalar product, all we're going to...
The last problem, what if you just put those vectors in a matrix and then you do the cross product multiplication? You get the same answer.
Yeah, we're going to put it in a matrix, but I'm going to show you an even easier way of doing it.
No, I'm talking about the last one that you just did, the area of the triangle.
Yeah, it's going to be the same idea.
Root 3 and then divided by 2, and that'll be the same thing.
Yeah, it's essentially the determinant.
Sine and the cosine angle and all that complicated stuff.
Yeah,
Can you do that?
you could. So we're going to write it as row vectors. 1, 3, 5. 2, negative 1, 0, and negative 3, 0, negative 1. All right, so each vector gets its own row. And again, I try to kind of flirt with linear algebra topics without getting too crazy into it, because in theory I should explain concepts like what is a determinant and where does it come from and what does it mean. For us, the concept of a determinant is really just simply defining itself as areas and volumes depending on the space that you're working in. All right. In linear algebra, you could represent vectors as either row vectors or column vectors within a matrix. In this context, we're just choosing to represent them as row vectors. All right. So what we do is we put this in our calculator and we find the determinant. So we're going to call this matrix A. The determinant of matrix A. All right, so that's what I'm going to show you how to do now. Because we already know how to put a matrix in. It's just a question of how do I find the determinant. All right, so second inverse brings up the matrix menu. Edit. We're going to select matrix A. Generally work out a matrix A unless we're operating upon multiple matrices. This one is a 3x3 matrix. So you're just typing in the rows and columns. And quit out of there, so second mode. And the whole purpose behind quitting out, again, is to avoid accidentally typing something in to the matrix itself. And then you're going to hit second inverse again, so back into the matrix menu. This time math. You see the option numero uno. It says determinant. And then you are going to go back into the matrix menu. So second, inverse, go to names, select matrix A. And as long as you type the matrix in correctly, you'll have precisely what you're looking for, which is the determinant of that matrix. So for our purposes, a determinant, all it means is the triple scalar product. What is a triple scalar product? It's a dot product after a cross product. All right. It's one of those things like, unfortunately, if you want to learn more, you got to take a linear algebra course. Most people are fine not knowing more though. Or taking the linear algebra course. I don't want to trivialize it. What I guess I meant to say is most people are satisfied with my answer. You have options. Those who don't want to know, you never have to know. Those who do want to know, there's a way to know. All right. So -8. -22?
Yeah, I got -8.
Interesting. Let us investigate. (135) 2 (-1 0) (-3 0 (-1). I think I typed it incorrectly.
I got it.
You got it? The -8, yeah.
My last one.
There it is.
No, I put the wrong value in the bottom of the quadrant. Once a
Alright, so the volume of a parallelepiped is really just the absolute value of the triple scalar product. So if a question were to ask you to find the volume of a parallelepiped, all you'd have to do is do what we just did, but if you got a negative, drop the negative. Alright, so that should be easy enough.
So I'm just going to put a star on number 10. Number 11, I'm going to put a star on it, and then just define very quickly what coplanar means. Coplanar is telling us all points, all vectors in this case, exist on the same plane. All right. If that's the case, then, and it's really kind of important to understand this, and this should, in theory, I mean, best laid plans, I guess, it should have come from the tech assignment, but when you have a parallelepiped, so you really have the 3 dimensions that make up your parallelogram in space. Let me just try to do that. You have the 3 dimensions that make it up in space. So the length, the width, and the height. And then from there, we kind of build outward to determine what your actual shape is going to be. All right. So in order for them to exist on the same plane, your parallelepiped must contain 0 volume. All right, because you're looking at the 3 important adjacent vectors that make up that triple scalar product, U, V, and W. I'll just denote them here. I'm just making up possible directions that they could go in. They have to give you the 3 dimensions of the parallelepiped. If it's going to exist in 3 dimensions, one of them has to be in the x direction or somewhat in the x direction, one of them has to be somewhat in the y direction, and one of them has to somewhat give it height, in the case of this diagram, somewhat be in the z direction. If you're all living in the same plane, you'd be looking at a parallelepiped with no height, all right, which would basically decompose into a parallelogram. It's kind of like taking that parallelogram or parallelepiped from that tech assignment
and smushing it down into the XY axis. Or doing what you did in the tech assignment, just skipping that last step where you created that prism that projected it out into 3 space. Everything that you did prior to that had it living in one plane. That just shot it up to meet whatever was point B. It brought it up, it projected it up to give it height. Alright? If it's coplanar, it would never have been projected up to give it height because vector W would be living in the same plane as U and V. Alright? Thereby giving you a 2-dimensional figure living in a 3-dimensional system. Alright? So, all this is telling you to do is use a triple scalar product, aka the determinant, and just root for 0 as a result.
So this plane in this question would be like at an angle?
It could be at an angle, but based on my drawing, you know, it'd be like pitched outward. It's
So
something.
that's have to be like less we did, just kind of tilted,
Yeah,
flat.
it could be something like that without any kind of height. Yeah. So it could be any kind of orientation. It could even be in the XY plane, but the bottom line is it wouldn't have any height based on its orientation. So if it's on a slant, it wouldn't have any thickness going in the height direction relative to its orientation. All right, so the last thing we're going to do is talk about the parametric equation of a line. And this is going to be very brief. Because all I want to do is define the equation of a line for you in 3 dimensions, and then I can give you some examples to work on your own and then get you out of here. So, define parametric equations for a line L that contains point P sub O, and then it's parallel to the given vector V. Use the fact that the displacement vector between the given point P sub O and arbitrary point P on the line must be parallel to that. That's like, okay, cool. You read words off a piece of paper for us. That's wonderful. An explanation, if you please. You know, so what that's saying is that you have some line in space. And I'll put some arrows on it. That is not an arrow. That line, by definition, has to be parallel to some given vector. All right, so I'm going to create a vector that we're going to call ABC, vector V. That's parallel to that arbitrary line. All right. So that line, pretend it's parallel. Make it look parallel on your papers, because apparently I can't draw parallel. Milk, eggs, and strawberries. Good to know. All right. So what we're getting at is that a vector parallel to ABC would have to be some kind of scalar multiple of ABC itself. All right. So all I have to do is create a vector living along that line. That we'll call that line L. All right, because they told us to. I'm going to plot 2 arbitrary points on that line. One P sub O, the starting point, and the other P. All right, and that's going to create a vector as a subset of that line. All right, what I want is the displacement vector between P and P sub O, or starting at P sub O. So P sub O going to P is going to be the difference between the values that make up P and P sub O. So X minus X sub O Y minus Y sub O, cripes, and Z minus Z sub O.
So if I multiply this vector v by some scalar, I should get p sub o p. All right? So that scalar that I'm choosing to multiply is a parameter. So I'm going to multiply it by a parameter that I choose to call t, because thinking back to the first unit, when we have parametric equations, we talked about time as being a parameter of some other kind of function. So if I have x and y, yeah, that's great. That'll give me the path. But if I wanted to find movement along that path, it's usually in terms of time. All right, so let t equal the parameter. And this is going to be a scalar. So, and what ends up happening here is that if I take vector v and multiply it by t, that was actually red, multiply it by t, I'm going to get a result of the displacement vector p sub o times p, times p, p sub o p. Now I could actually carry out the process because v is ABC, so I could say TA, TB, TC is going to be equal to all this jazz up here, P sub OP. All right, now if there's going to be equality here, then t times a should be equal to x minus x sub o. That's where our first formula comes from. So I can make a little note here. And I won't take you through each of them, but I'll just show you this case. TA would be equal to x minus x sub o. If I add x sub o to both sides, that's going to give me, as a result, x equals x sub o plus TA. Which is actually my first rule. All right? You do the same thing for TB equals y minus y sub o. You'll get the second part of the rule. And then TC is equal to z minus z sub o, all right, which gives you the third part of the rule. All right. So the vector form of a linear equation actually ends up being the three components put together: x, y, z, x sub o plus TA, comma, y sub o plus TB, comma, z sub o plus TC. And we're actually not going to worry about the symmetric equations.
Plus C sub o? Or no, just the three together.
Yeah, just the three together, yeah. No, that's cool. Well, I guess you don't have to scribble it out. We're just not going to bother with it. I mean, those are the rules that give us the symmetric form. There's just not much we're going to do with it. So I guess I don't need to scribble it out. I'm just not going to do anything with it. But if you want to scribble it out, by all means. You're generally scribbling stuff out. It just looks ugly enough. But you can write a little note, disregard, because all this is each one of these equations solved for t and then set equal to one another. I don't think you need to define it in any particular way in order to come up with those rules. So any question that asks you to come up with symmetric equations, we're not going to bother with.
we only care about the parametric equations because what we end up here with are vectors that involve variables, not just scalars. All right? Sorry. So there are going to be variable vectors, which are known as vector valued functions. And these are the things that we're going to be able to do calculus to. And we're going to have to be able to kind of take our knowledge of vectors in their scalar form and apply it to function-related vectors and then go from there. So a lot of interesting stuff coming ahead. But what I would want you to try to do is see if you could figure out the solution to numbers 1 and 2 on your own before I go through the process for you, just using these ideas. Because if you could figure it out, I mean, I could give you the same spiel every single time. If you could figure it out before I end up spoiling it for you, then you're already ahead of the game. All right. So if you can't, that's fine. This is where we'll pick up next time. But at least give it a shot. A little tip, A, B, and C represent the parallel vector. So the idea would be that if somewhere along the lines, you're going to have to figure out a vector that corresponds with these 2 points. So that's a good place to start. All right, and then if you don't get beyond that, that's fine. We'll pick up with it next time. But if you do, then you'll be ahead of the game, like I said.